When you look at America's first skyscrapers, these soaring monuments of steel and ambition, there's a question almost no one thinks to ask. Where did all the waste go? And how did it travel down 10, 15, or 20 stories? In 1885, a single Chicago high-rise could discharge 180 gallons of sewage per minute into city mains barely built to handle more than that. Engineers panicked. The physics of gravity turned ordinary plumbing into something genuinely dangerous, siphoning water seals dry, forcing toxic gas into occupied offices. The hidden challenge of removing sewage from these towers nearly undermined the entire skyscraper revolution before it began. And the desperate solutions they pioneered still sit inside every high-rise you've ever set foot in. In 1884, William LeBaron Jenney stood at the center of a construction site on LaSalle and Adams in Chicago, holding plans for a building that would soon rise 10 stories above the street. The home insurance building was unlike anything the city had seen. Its steel skeleton promised fireproof safety and an unprecedented lightness, but inside, a different kind of problem demanded attention. For the first time, every floor, 10 in total, would be stacked with offices, each equipped with flush toilets and running water. All of that waste had to go somewhere. Jenney's solution was as bold as the steel frame itself. Instead of the small 4-inch house drains used in the city's low-rise blocks, he called for a single massive cast-iron pipe, 12 inches in diameter, with walls 3/4 of an inch thick. This pipe, known as the soil stack, would run straight through the core of the building, dropping 138 feet from the top floor to the sewer below. It was a vertical shaft large enough for a grown man to crawl through, engineered to handle the combined flow from every fixture, sinks, toilets, urinals on every floor. The scale was radical. No American building had ever needed a drain this size. Jenney worked closely with his plumbing subcontractor to calculate the load. At peak times, the tower could discharge nearly 200 gallons of waste per minute, a volume that would overwhelm any ordinary pipe. The 12-inch stack was not just oversized, it was essential. Too small and the rushing water would create a vacuum, pulling the water out of fixture traps and allowing sewer gases to surge upward. Too thin, and the pipe could burst under the combined weight and pressure, flooding the lower floors with waste. Every joint in the stack was sealed with molten lead and oakum, then reinforced with heavy flanges, each bolt torqued to withstand the building's daily cycles of use. The pipe's sheer mass, hundreds of pounds per section, required teams of laborers and a system of block and tackle to hoist each length into place. As the building rose, so did the stack, floor by floor, until it pierced the roof and vented above the city skyline. Jenney's 12-inch waste shaft was a silent engine that made the skyscraper possible. Without it, the promise of vertical living would collapse under its own waste. The engineering challenge was invisible to most, but it set the stage for a new kind of building, one where the real drama played out in pipes and shadows, deep inside the walls. Before tall buildings transformed city skylines, plumbing in American cities followed a simple, predictable path. Most structures were 2 to 5 stories, built of brick or stone, with each floor draining wastewater through short, horizontal pipes. These pipes, known as house drains, rarely exceeded 4 inches in diameter. Wastewater from sinks, tubs, and early flush toilets would flow by gravity into a main drain, then out to the street where it joined a slightly larger municipal main, usually 6 to 8 inches wide. In residential neighborhoods, these mains ran beneath the pavement, designed to carry the combined flow from dozens of houses at a slow, steady pace. The typical house drain was cast iron, sealed at the joints with oakum and molten lead. Its size reflected the modest volume it carried, a handful of fixtures used sporadically throughout the day. Even in a busy boarding house or hotel, the peak flow rarely strained the system. Water closets, still a relative novelty in the 1870s, were often limited to the ground floor or basement, where gravity did most of the work. The physics were straightforward. Wastewater dropped only a few feet from fixture to drain, then traveled horizontally toward the sewer. The short vertical runs meant that air pressure inside the pipe stayed stable, and siphoning, the unwanted suction that could draw water out of traps and let sewer gas leak back, was rarely a concern. Municipal engineers designed the city's main sewers to match these patterns. A 6-inch main could handle about 5 to 10 gallons per minute per household, more than enough for the daily ebb and flow of a block's worth of homes. The largest pipes, 8 inches in diameter, served commercial districts or clusters of hotels, where the load might spike during morning or evening rushes. Still, these were rare surges, quickly absorbed by the system's built-in capacity. Maintenance was mostly a matter of keeping tree roots and debris from clogging the pipes. There was little need to think about pressure surges or the complex effects of gravity on long vertical drops because the buildings themselves simply weren't tall enough to create those problems. In this low-rise world, the plumbing systems were as much a part of the city's invisible infrastructure as the sewers themselves. Their limitations were clear, but manageable. The jump to 10 stories and the challenge of moving waste safely from such heights would demand a new kind of engineering, one that pushed beyond the familiar boundaries of pipe and flow. Ellis S. Chesbrough, Chicago's chief engineer, faced a city on the brink of sanitary crisis. By 1885, the skyline was rising, but the city's sewers below were designed for a much smaller, slower flow. The new skyscrapers threatened to pour hundreds of gallons of waste per minute into mains built for the gentle trickle from houses. City records from that spring show urgent meetings in the council chamber, as engineers warned that a single 10-story building could discharge nearly 200 gallons per minute, almost double what the largest city main could safely carry. The established rule, written into the 1885 sanitary ordinance, set a hard limit. Any building over 55 feet tall had to meet stricter requirements, both in pipe material and in how it connected to the city's network. The ordinance demanded cast iron for all drainage pipes in tall buildings and required that stacks be vented to the atmosphere, a direct response to mounting reports of foul air and unexplained illness in the new towers. Chesbrough's calculations made the stakes clear. At peak times, a single skyscraper could send a surge of waste that rivaled the combined flow from an entire residential block. The city's 6-inch and 8-inch mains, designed for 180 gallons per minute at most, were now expected to absorb sudden spikes up to 200 gallons. Any higher, and the risk of backflow, pipe rupture, or overflow into baselines increased sharply. The 55-foot rule was more than a technicality. It was a line drawn to prevent the city's infrastructure from being overwhelmed. City inspectors now had authority to halt projects or demand redesigns if the planned discharge exceeded safe limits. The ordinance also shifted responsibility. No longer could building owners treat sewage as a private concern. The city itself set the standards, and compliance became a matter of public health. Chesbrough's office reviewed every new high-rise plan, checking pipe sizes and connection points against the city's capacity tables. When plans failed to meet the new standards, permits were denied or construction halted until corrections were made. The legal framework transformed skyscraper plumbing from a hidden, internal matter into a city-wide challenge. Every new tower forced a recalculation, not just of its own pipes, but of what the city itself could bear. The invisible contest between vertical ambition and horizontal capacity would shape every ordinance, every engineering calculation, and every risk taken as the skyline grew. 100 feet above the city streets, a column of wastewater plunges through darkness. In the confined shaft of a skyscraper, gravity does more than pull water downward. It unleashes a force that few plumbers of the 1880s had ever calculated. As soon as a toilet flushes on an upper floor, water accelerates in the vertical stack, gathering speed until it reaches nearly 2 feet per second by the time it nears the basement. This velocity is not just a number. It means that inside the pipe, the falling water creates a powerful suction behind it and a surge of pressure at the bottom. The difference in pressure, what engineers call delta P, can be enough to pull the water out of fixture traps or, if unchecked, to send a shockwave back up the stack. The physics are relentless. In a 10-story building, a full column of water can drop with such force that, if the pipe is too narrow or the venting inadequate, the air inside is drawn downward at high speed. This sudden rush of air can strip the water seal from traps on the upper floors, leaving nothing to block the rise of sewer gases. The infamous MIA, hydrogen sulfide, methane, and other noxious fumes, finds its way into offices and corridors, carried by the same forces that were supposed to flush it away. But suction is only half the danger. At the base of the stack, the water's momentum slams into the horizontal drain, forcing pressure back up the system. If the city sewer is partially blocked, or if the waste stack is undersized, this back pressure can blow water out of lower floor fixtures or even crack the pipe itself. Contemporary engineering handbooks warn that a 100-foot drop could generate dynamic pressures far greater than anything seen in a low-rise house. The equation delta P equals water density times gravity times height minus half the density times velocity squared became the silent law inside every skyscraper wall. For the men who designed and built these vertical shafts, every calculation was a wager against disaster. One misjudged diameter or an unvented branch could turn a modern marvel into a chamber of foul air and flooded basements. The solution would demand more than brute strength or thicker iron. It would require a new kind of hardware, one that could tame the invisible forces racing through 100 feet of pipe. By the late 1880s, cast iron pipe manufacturers faced a new kind of demand from architects and engineers. The home insurance building had proved that only a massive, thick-walled pipe could control the surge of wastewater in a tall structure. But producing such a pipe was no ordinary task. The American Cast Iron Pipe Company, founded in 1888, stepped in with a product that set the standard for the era's high-rise plumbing, the so-called skyscraper pipe. Each section of this pipe measured 12 inches across, with a wall thickness of 3/4 of an inch. The dimensions were not arbitrary. Engineers calculated that only a pipe of this size could keep water velocity below the 2 feet per second threshold, where dangerous suction and pressure spikes would threaten the traps on every floor. The cast iron itself was poured into sand molds, then cooled and machined to exact tolerances. The finished product weighed hundreds of pounds per length, a mass that dampened vibration and reduced the risk of cracks from the building's natural sway. The pressure rating was just as important as the diameter. Factory tests subjected the finished pipe to hydrostatic pressures of up to 150 psi, far higher than any load expected in daily use, but essential for withstanding the unpredictable surges that could occur in a fully occupied office block. This margin of safety was critical. A burst soil stack would mean not just a flooded basement, but potential structural damage and costly repairs. Fire resistance became a key selling point. Unlike lead or tin pipes, which could melt or deform in a building fire, cast iron would hold its shape, containing both waste and any dangerous gases that might accumulate inside the stack. The American Cast Iron Pipe Company's marketing materials boasted of this dual strength. Their pipes could bear any load a modern tower might demand and would not yield to flame. The oversized soil stack was more than a technical fix. It was a new kind of backbone for the skyscraper, one that carried not just waste, but the confidence of every engineer who signed off on a building permit. Each pipe, tested to its limits, became a silent guarantee that the new vertical city would not be undone by the invisible forces rushing through its core. As the codes of the next decade would formalize, the oversized cast iron stack was no longer an experiment. It was the new rule. William H. Channing approached the skyscraper's plumbing problem with a scientist's eye for detail. In 1892, he published The Plumbing Engineer's Handbook, a volume that replaced guesswork with calculation. Channing's tables linked every fixture in a building, every toilet, sink, and urinal, to a number he called the fixture unit. This unit served as the backbone for sizing stacks, translating the chaos of daily use into predictable flows and pressures. Each fixture added to the total, and the table specified exactly how wide the soil stack needed to be and how long it could run before the risk of siphonage or back pressure became unacceptable. For skyscrapers, Channing set a hard limit. No single vertical soil stack should exceed 150 feet in height without relief. This figure was not arbitrary. It came from careful measurement of water velocity, pressure drops, and the cumulative effect of dozens of simultaneous flushes. The 12-inch diameter, already adopted by Jenny and the American Cast Iron Pipe Company, found mathematical backing in Channing's charts. His calculations showed that only a pipe of that size could keep water speeds below the 2 feet per second threshold, fast enough to clear waste, but slow enough to avoid stripping the water seal from every trap in the building. Channing's tables also introduced a safety factor. He assumed peak usage far above the daily average, building in a margin for the unpredictable surges that came with lunchtime or closing hour. This approach gave engineers confidence that their designs would hold up not just in theory, but in the unpredictable reality of a crowded office tower. The fixture unit method quickly spread to city ordinances and became the standard for plumbing engineers nationwide. With Channing's numbers, the invisible world inside the walls became legible, measurable, and most importantly, safe. The era of trial and error gave way to a discipline where every pipe, every joint, and every vent was sized by calculation, not by hunch. The skyscraper's sanitary core, once a source of panic, now rested on a foundation of numbers and charts. By the late 1880s, the fear of sewer gas was as thick in the air as the smoke from the city's chimneys. In the heart of Manhattan, the World Building stood as a symbol of progress, 20 stories of glass and iron, crowned by Joseph Pulitzer's Golden Dome. But inside, a different story unfolded. On the upper floors, clerks began to complain of headaches and nausea. The culprit was invisible but unmistakable: hydrogen sulfide, the rotten egg stench of sewer gas, drifting up from the vertical stacks. Health inspectors measured concentrations as high as 35 parts per million, enough to trigger alarms in today's laboratories. At those levels, even a brief exposure could cause dizziness, eye irritation, or worse. Newspaper headlines fanned the panic. The New York Sun ran stories of asphyxiating vapors infiltrating the city's tallest towers, quoting tenants who described the air as poisonous and unfit for human breathing. In Chicago, the Tribune warned that the city may be fireproof, but it is not gas-proof, and called for immediate action to protect office workers from the silent threat rising through their walls. Letters to the editor demanded to know why architects had conquered fire and gravity, but not the menace lurking in the drains. The World Building was not alone. Across the country's new high-rises, reports of sewer gas outbreaks became almost routine. Building managers tried to mask the smell with camphor and coal tar, but the symptoms persisted. Doctors linked mysterious outbreaks of illness to the presence of foul air on upper floors, fueling public suspicion that skyscrapers were breeding grounds for disease. The fear was not just about discomfort. It was about the possibility of mass poisoning or even death if the gas built up undetected. The pressure on city officials and engineers was immediate and intense. The public demanded a solution that would make these modern towers not just marvels of steel and glass, but safe places to live and work. The answer would require more than bigger pipes or thicker walls. It would demand a new way of thinking about air, water, and the invisible danger that haunted the vertical city. Thomas Crapper's name became synonymous with the modern water closet, but his real breakthrough lay in a deceptively simple device: the water seal trap. By the late 1870s, the dangers of sewer gas were well known, but the technical solution remained elusive. Most early traps, simple S-bends, failed under the pressure swings inside a tall building, their water seals sucked dry by the rush of wastewater or blown out by back pressure at the base of the stack. The result was a direct path for noxious gases into every office and corridor. Crapper's answer was the U-bend, soon refined into the P-trap, a curved section of pipe that held a stable 2-inch deep pool of water. This water formed a physical barrier, blocking gases from traveling up the drain. But in a skyscraper, even the best trap could be defeated by the powerful suction created during a heavy discharge. Crapper's 1887 patent addressed this flaw directly, specifying that every trap must be vented, connected by a separate pipe to the open air above the roof. The vent allowed air to flow freely into the drainage system, equalizing pressure and preserving the water seal, even as hundreds of gallons per minute shot down the main stack. The technical details mattered. Without at least a 2-inch water seal, the trap could not resist the negative pressure generated by a full-bore flush on the upper floors. Vent pipes, sized according to the new codes, had to rise unbroken above the roof line, releasing any gases safely to the atmosphere. The 1890 New York Code Amendment, following the world building's venting crisis, made these requirements law. Every drainage stack with 3 or more branch intervals needed a dedicated vent, and every fixture required a properly vented trap. Field tests in Chicago and New York confirmed the effectiveness of the new system. Buildings retrofitted with Crapper's vented P-traps saw odor complaints vanish almost overnight. Engineers documented that even during peak usage, the water seal remained intact. The combination of a reliable 2-inch trap and a continuous vent stack transformed the skyscraper from a vertical hazard into a safe, modern workplace. Crapper's invention, codified in patents and ordinances, became the unseen safeguard in every high-rise bathroom, a quiet victory of engineering over invisible danger. Supplying clean water to the upper floors of America's first skyscrapers proved just as daunting as removing waste. In Chicago, the city's water mains could only push water to about 60 feet, roughly the height of a 6-story building, before the pressure dropped below 15 pounds per square inch needed for faucets and toilets to function. Anything higher left office workers and tenants dry, no matter how advanced the plumbing below. The Board of Trade building, completed in 1889 and rising 14 stories, offered a bold solution. Engineers installed a 30-horsepower steam pump in the basement, designed to force water up a vertical shaft to a cistern perched on the roof. This rooftop tank, holding up to 10,000 gallons, acted as a reservoir, using gravity to feed water back down to the upper floors at reliable pressure. The pump's daily routine was a spectacle of power and risk. Steam engines fed by coal and watched by round-the-clock attendants drove pistons that hammered water up more than 180 feet. When the pump operated at full capacity, it could fill the rooftop tank in just a few hours. But any drop in steam pressure or a minor leak in the system could leave entire floors without running water until repairs were made. Maintenance logs from the period record repeated near failures, valves sticking, pipes rattling, pressure gauges swinging wildly as the system strained to keep up with demand. The rooftop tank, visible from blocks away, became a symbol of the building's hidden complexity. Its iron bands and wooden staves held back a weight that, if released suddenly by a burst pipe or broken valve, could flood the upper stories in minutes. Supplying water above the 60-foot limit had become an engineering contest as fierce as the battle against gravity below. Every flush, every turn of a tap on the top floors depended on the silent, relentless work of steam, steel, and the men who kept the pumps running. Molten iron poured into sand molds at the American Cast Iron Pipe Company's foundry transformed raw metal into the backbone of the vertical city. Each 12-inch pipe section began as a glowing cylinder, cast with walls 3/4 of an inch thick. The sand mold process allowed for smooth interiors and precise contours, crucial for maintaining steady flow and preventing buildup along the pipe's length. Once cooled, the pipes moved to the machine shop, where lathes shaped the flanges, broad collars drilled to accept heavy bolts. These flanges, paired with thick rubber gaskets, formed joints that could withstand both vibration and the surges of pressure that ran through a fully occupied building. The scale of these pipes was unlike anything used in low-rise construction. A single 12-inch section could weigh more than 400 pounds, demanding a team of workers and a block-and-tackle rig just to lift it into place. Each joint was packed with oakum, tarred hemp fibers, then sealed with molten lead, creating a watertight barrier that resisted both leaks and chemical corrosion. The finished stack, when assembled, formed a rigid fire-resistant column from roof to basement, able to carry hundreds of gallons of waste per minute without warping or cracking. Durability was not a luxury, but a necessity. Factory hydrostatic tests subjected every length to pressures up to 150 psi, far greater than any daily load. This margin of safety reflected both the unpredictable nature of high-rise plumbing and the unforgiving consequences of failure. The cast iron's mass dampened noise and vibration, earning it the nickname the quiet pipe among engineers. For the early skyscraper, the craft of pipe making was every bit as vital as the steel frame overhead. The unseen artistry of the foundry and machine shop became the silent guarantee that the modern city could rise and stay sanitary, floor after floor. John O'Connor's hands were stained with iron filings and pipe grease, his boots slick with the runoff of molten lead and wastewater. For $3.25 a day, he climbed the scaffolds inside Chicago's first skyscrapers, guiding cast iron pipes into place while the city's business elite hurried below, unaware of the dangers overhead. O'Connor's diary, now tucked away in a Union archive, describes the daily hazards: balancing on narrow beams to bolt flanges, inhaling the sharp tang of sulfur from open vents, and feeling the building sway beneath his feet as he hammered joints tight. On the coldest mornings, steam from the rooftop pump rooms mingled with the breath of men hauling pipe sections that weighed more than 200 pounds each. The labor was relentless. Each length of soil stack demanded a team, one man to steady the pipe, another to pack oakum into the joints, a third to pour the lead that would seal the system against leaks and gas. O'Connor wrote of the constant smell of sulfur and the headaches that followed a day spent in the cramped shaft. 12 cases of illness were recorded among his crew that winter: nausea, dizziness, and the lingering coughs that came from working in air thick with dust and sewer gas. Safety gear was rare. A slip of the hand or a falling coupling could mean a crushed finger or worse. Yet O'Connor's pride was clear. The finished stack was more than a job. It was a promise that the city's newest marvel would stay clean and safe. The plumbers who risked illness, injury, and exhaustion to build these hidden systems left behind more than pipe and solder. Their work became the silent backbone of the modern skyscraper, a legacy forged one joint at a time, high above the city streets. Modern plumbing codes still carry the DNA of those first skyscraper experiments. The International Plumbing Code, adopted in cities across the United States, spells out rules that trace directly back to the calculations of Jenny, Channing, and their peers. Section P109.0 sets a minimum stack diameter, 12 inches for any building over 10 stories, echoing the oversized pipes first lifted into place in 1884. The code is precise. No exceptions for smaller buildings, no shortcuts for new materials. The diameter is not a suggestion, but a hard threshold rooted in the physics of water velocity and the dangers of trap siphonage. Venting requirements are just as strict. The International Plumbing Code mandates that every vent stack must rise at least 6 inches above the roof line, ensuring that sewer gases can escape safely and that air can flow freely into the system. This rule descends from the 1890 New York Amendment, which responded to real-world crises in the world building and others. Without this vertical rise, negative pressure could strip water from traps, opening the door to the very hazards that haunted 19th-century towers. The code also demands that every fixture, every toilet, sink, and urinal connect to a water-sealed trap with a minimum 2-inch depth, The legacy of Crapper's U-bend, refined and enforced, remains a silent guardian in every bathroom. Even the spacing of relief vents, required every 10 floors, comes straight from Channing's tables. What began as desperate improvisation became the backbone of a national standard, written line by line into the rules that govern every new high-rise. These regulations are not relics, they are living echoes of the early towers, still shaping the unseen systems that keep modern cities clean and safe. The skyline of the American city is often celebrated for its steel and glass, its soaring ambition, and the architects who dared to build ever higher. Yet the true genius of the early skyscraper lies just as much in what cannot be seen. Every modern high-rise is a quiet monument to those first, oversized soil stacks and the careful calculations of engineers like William H. Channing. The Plumbing Engineer's Handbook, published in 1892, captured this invisible achievement. The unseen pipes, properly sized and vented, are as essential to the safety of the building as the steel frame itself. Today, few pause to consider the legacy running behind the walls and under the floors. The code-mandated 12-inch stack, the vent rising above the roofline, the 2-inch water seal at every fixture, these are not just technical details, but the living bones of the vertical city. The lessons learned in the Home Insurance Building, the Board of Trade, and the World Building still guide every plumber, inspector, and engineer working on a tower today. Modern architects may draw bold lines across the horizon, but the quiet discipline of sanitary engineering remains at the heart of the city's health and comfort. The next time water vanishes with a flush from the 50th floor or fresh water arrives on demand, it is worth remembering that these ordinary miracles are the product of a century-old struggle with gravity, pressure, and the unseen forces that shape urban life. The skyscraper is not only a triumph of height, but a triumph of the hidden systems that let people live and work, stacked safely above the street. Today, every high-rise flush and faucet depends on systems first conceived to stop disease and disaster in America's earliest skyscrapers. As cities push ever higher, now with over 100,000 buildings above 12 stories nationwide, the invisible infrastructure beneath our feet becomes more critical than ever. The battle for clean, safe, and sustainable urban plumbing isn't history, it's a daily engineering challenge. The tallest dreams still stand on what no one sees. Share your thoughts on modern skyscraper living below.